right, so we'll start again. So matter, all matter in the universe is made up of atoms. I shouldn't say that. That's not entirely correct because there's matter in the universe that's made up of subatomic particles, particles that are smaller than atoms. And so what we're interested in is not really the subatomic particles, because the subatomic particles, of which there are three main ones, the proton, neutron, electron, which we'll talk about later. But that's about it. What gives the richness of chemistry is having all these atoms. When we put together the subatomic particles to make an atom, we see a lot of different atoms. We have small atoms like helium, and big atoms like francium. In fact, the radii, it's hard to come out, because the radii you're going to see vary depending on radiuses that vary a little bit here. Helium should be the smallest, although this is weird looking arrangement here. But we have one in the book. I should jump ahead, but I'm not going to jump ahead. I just grabbed this one because it's quick. And so we have atoms of different sizes, but we also have atoms of different behaviors, different properties. And so just like there are different kinds of dogs, there are different kinds of atoms. And so what we want to do is we want to learn about, the personalities of the atoms, right, or the elements, just like we would want to know the personalities of different breeds of dogs. This kind of stuff. And so we'll be learning more about these atoms here. The atoms make up.
Why doesn't that one at the bottom row without
This bottom row here?
Yeah, francium.
Okay, it also depends on the time that this was developed. One thing is these radioactive atoms, some of them, in fact, all of them after uranium are man-made. They make these radioactive atoms by taking smaller atoms and fusing them together in one of those atom smasher colliders. And so they'll fuse together, but what they make is unstable. It's like a monster atom in a way that it's unstable, and then it just breaks apart again. And it breaks apart into other things. And so radioactive atoms are very hard to take measurements of because some of them have these things called half-lives, in which half the atoms are gone at a certain time. These half-lives are on the order of anywhere from microsecond, one millionth of a second, boom, half of them are gone. So you're taking a measurement, you gotta be quick, right? And so francium, this is why you'll see a lot of these numbers in parentheses. These estimates, but they probably haven't done proper measurements for the size. Francium's the same as well. That could be one reason. Some things have a longer half-life and they can measure it. Other things. Or the other reason is it's too much data. So it's like a bridge dictionary versus a complete dictionary. You don't want to be lugging around. So they just try to clean it up. And so they'll eliminate some stuff. previous data. We could try to look it up. Maybe somebody's tried to do some measurements. But it would be great to use theory, wouldn't it? I want to ask you, can you use some theory and tell me the diameter of a helium atom? You know? Question? 1 angstrom? Actually, less. But I mean, how can you use some theory? Well, one, what is the theory? You know, I just told you matter consists of atoms, but is that it? You know, is that really a good detailed description of matter? And then everything else we have to measure. Everything else we have to observe. In other words, you know, okay, this is better. Yes. The other one, there's a mistake, you know, that this one looks better. I feel much more comfortable with this chart, but that happens, you know. It's nice.
Is there a barrier on the periodic table that shows what naturally occurring elements there are? Like which ones are not man-made? Like which ones do you find out in space and stuff, or is it just kind of all scattered?
It's all scattered. It's all scattered because of this. As we'll learn later on, you would think that, you know, all the oxygen atoms and all the hydrogen atoms that make up this water are identical. They aren't. And you would think that all water molecules in this would weigh exactly the same as any other water molecule. They don't. There are some water molecules in here that are heavier than others. Why? Yeah, their atoms are heavier. And so what it turns out is this. Like in nature, we'll find, and that's what this number here is. This number is coding for something called isotopes. And so the most abundant hydrogen atom in there is H1. And then there could be some H2. In fact, you did drink some H. If you drank some water today, you had some H2, which is an atom of hydrogen that's twice as heavy. And there's something called H3. H2 they don't call hydrogen anymore, they call it deuterium. And H3 they call tritium. H3 is a radioactive hydrogen atom. And so, yeah, there's radioactive oxygen, there's radioactive nitrogen, there's radioactive carbon. Have you heard of carbon-14? Carbon-14 is radioactive. It occurs in nature. And so since there are things that exist. But however, all isotopes of uranium are radioactive. It doesn't matter. All atoms of uranium are radioactive. So basically it's from these heavy elements, starting with, actually before uranium, you know, starting from like polonium. Like here's lead, bismuth, polonium. Polonium's radioactive. Actinium's radioactive. Radon, you might have heard of radon. Radon, yes. It's radioactive. And so it tends to be the heavier ones, and then there are radioactive man-made ones. Carbon-14 is not man-made, though. Carbon-14 is made by natural cosmic radiation processes. But we'll learn more about that as we go on. So this is one of those patterns that you kind of memorize, but you know we don't call it a law. You know, just kind of get a feeling for it. It's one of those like personality of the elements. The other thing you have to keep in mind, so we did this little exercise, this little quiz, which is, you know, I just want to see this is a good exercise, and, you know, you want to think about, some people say what you need to do is you need to, you know, close your eyes and then, you know, tell me what it is, rather than look at something. And if you could do that, then you're visualizing material. When you visualize material like that, it makes it easier to remember. Especially if it's in your own words. So that's what the little quiz was. The other thing is, though, that could be your visualization, but you're going to be challenged on it. And this happens in science in general. This is why there's exams in this class. A lot of people say, "Why are there tests?" Let's not have any tests. But science is always being, there's testing that's always being done. Even when you're done with all your classes, you send out, if you have some research that you're doing, you send it out to what we call referees. The referees are your peer reviewers. The referees are going to grade your material, kind of thing. Is it good enough to be? Some of the referees are very tough. So, for example, if you try to publish in a journal like Nature or a journal like Science, top-end premier journals, those referees have a very high standard. They aren't going to let weak stuff slide through, or something that's not so significant slide through. But there's all levels of journals. There are non-refereed journals, but non-refereed journals people shy away from because non-refereed journals or non-peer reviewed material, anybody can say anything without being called out on it. And so what you need that refereeing process. So you want people to call you out. So if you say that I believe atoms exist, you have to be prepared to defend that. Just as Dalton, who proposed it, was able to do. All right, then, we're studying matter, so we can look at it at different levels. We can look at it at the macroscopic, the microscopic, or the particulate level. But one of the things we notice is that there are different states of matter. The states of matter would be like solid, liquid, gas. Those are the states. All right, when we're looking at the different states of matter, we can delve into it theoretically, a little bit of the theory of this. And the theory that defines what state it is. For example, some things can transition from state to state, like water. You can freeze water down, you can warm it up, you can boil it to a gas. So water can go through all three states easily. Actually, there's a fourth state of matter. This fourth state of matter is one of the most abundant states of matter. Do you know what it is, the fourth state of matter? Plasma, right? Do plasmas exist here on Earth? Yeah, actually, there's two types of plasmas. The sun is an example of plasma. That's called a thermal plasma, an equilibrium plasma. We have these. The fluorescent lamps here, the gas inside that tube is a plasma. And so what's happening in there is this little lightning bolt that's going through the tube. It's a very controlled lightning bolt, not an out-of-control lightning bolt. Lightning bolt would be another example of plasma. A flame would be a plasma. And so if you take a gas and then just continue heating it up, you'll eventually form a plasma, which we'll talk about later. And all this comes from kinetic molecular theory. This is kinetic molecular theory. This is a theory that's trying to give us a more fundamental description of what a solid is, what a liquid is, what a gas is. So that's what we're talking about here. And kinetic means motion. Kinetic. Like we have the kinesiology majors here. They're interested in motion. Motion. Molecules, motion of molecules. This is motion of molecules theory. And so basically it boils down to this. Temperature. If something's hot versus something's cold, let's say you take a cold piece of copper, the copper atoms aren't fixed, they aren't stationary. At room temperature, the copper atoms are vibrating. As the temperature gets hotter and hotter, the copper atoms vibrate with more energy. And so we're just looking at temperature. Temperature is a measure of the motion. In other words, temperature is a measure of the kinetic energy. Kinetic energy is the motion, energy of motion. And so if we cool it down, what happens to the motion? It slows down. And eventually, we'll hit a point where we cool it down and it just comes to a stop. When the atoms come to a stop, what is the temperature? Is it, you would think the temperature, is it infinitely low, or is there some finite limit? You know? Do we have to cool the temperature down to infinite, minus infinity Fahrenheit? No. Actually, we only have to cool it down to minus 273 Celsius, or minus 464 Fahrenheit, and then the atoms stop. And that we call absolute zero, so you know. Absolute zero is when the atoms stop moving.
Is it different for material?
No, it doesn't matter. It could be a piece of copper like this. Water, on the other hand, consists of molecules. Copper, actually, let me show you copper. That's probably easy to visualize. How are the atoms put together in copper? You know, we're interested in the composition of copper. Well, copper consists of copper, pure copper, unless we're looking at brass. If we're looking at brass, then it's not pure. And so we're interested in the what we call the structure, and these are the crystal. We call it a crystal structure because copper forms beautiful crystals, although sometimes they're hard to see. This is how the copper atoms are put together. Copper. There's a little, I guess, M&M. So the atoms are in motion. We can actually see the motion. Did I showed you the X-rays? Remember with the ovals? That's because of the motion at room temperature. If we froze that down to 0 Kelvin, those would not be ovals, those would be spheres instead. And so if we were to look at the actual crystal structure of this, these would be oval because, you know, it's like a blurred picture. You know, we're taking a picture of the atoms using X-rays. And it's like a super long exposure because what you have to do when you measure it is you move the detector around, catching all the X-rays that come scattered off there. When we look at an object like this, light hits it, you know, and we get light scattering off this, but our eyes, you know, refocus that light into an image that we see. See, this is an image. So this is another thing people are trying to figure out. You know, glass, you can make a lens out of glass. And so you could use glass to refocus into an image, like in a telescope, something like that. But glass doesn't work for X-rays. X-rays, or they'll, I don't know, I guess it depends on the wavelength. And so people are looking for lenses that would refocus. If there's a lens that refocuses X-rays, then you could do that. You could shine X-rays on it. With this lens, you could actually see the image. You know, that would work. You know where you put that lens. That would allow you to actually see. And so one of the research projects in the materials department at UCSB, they're looking for something called a second harmonic generator, which would act as a lens for X-rays. Because if they could develop that, it would be a huge jump in technology. But anyway, getting back to this, it doesn't matter the material. So for copper, the vibrations, you know, in this, we call this a lattice, would stop. For water has 3 types of motion. There are 3 types of motion, if we break it down. One type of motion is the vibration. This is called vibrational motion or vibrational kinetic energy. So water molecules vibrate, like the hydrogen atoms and the oxygen atoms vibrate. You would think they could vibrate in an infinite number of ways, but there are only 3 ways the water molecule can vibrate. They have this kind of action, they have this scissor kind of action, they have this kind of action. There are only 3 ways of water. That means, like, if you were to heat up water, it's very interesting. If you were to heat up water, each of those ways that it vibrates consumes a specific amount of energy, a specific, what we call, frequency of energy. And so a lot of that energy is wasted because it doesn't hit the resonant frequency of the water. You know, have you heard of resonance? Certain things will, like if you hit an object and it rings, like you get that ringing tone, that you hit the resonant frequency. Sometimes you hit some object and it just thuds. And when you hit that and you get that ringing tone, that energy is absorbed, dissipated. There's but anyway, getting back to water. The vibration, the same thing happens with copper. This is all in the theory of chemistry. You know, these vibrations were actually predicted in chemistry to explain the lines. You can look at a animation. These are called normal modes of water.
Here in the unit, you'll study a system with 3 pucks. There are potentially 6 degrees of freedom here, but keeping the displacements to the line of the springs means that the symmetry of the system restricts this to 3 degrees of freedom, for which there are 3 normal modes.
If you have 3 objects like that, they can't vibrate any way they want. They only can vibrate in 3 ways. These are the 3 ways it can vibrate. And they correspond to different energies, so they'll absorb this energy, this
Let's
energy.
return to the behavior of water molecules that were introduced at the beginning of this video band, and examine the way in which they can be excited by 3 particular microwave frequencies. A water molecule is composed of 2 hydrogen atoms together with a single oxygen atom. So each water molecule is called H2O by chemists. Although quantum mechanics is the only accurate description of molecules, insight can be gained by considering a Newtonian mechanics model. You can represent the forces between the atoms as springs. Chemists usually represent molecules by what's called a ball and stick model. Now, although the water molecule has 9 degrees of freedom, which give rise to 9 normal modes, 6 of these are trivial, in which the particles move as if they're part of a rigid body. But there are 3 non-trivial normal modes. The smallest normal mode angular frequency corresponds to the normal mode where 2 hydrogens swing from side to side, each with a sinusoidal motion. Note that the oxygen atom hardly moves, since it's about 16 times more massive than each of the 2 hydrogens. A second normal mode has the hydrogens oscillating in step with each other, along the bonds, again at microwave frequencies. We should also say that in this animation, these oscillations are not only being slowed down, they're also being wildly exaggerated, as the movement would be minute compared to the length of the bond. Then finally, there's a resonant frequency in which the hydrogen atoms again oscillate in and out, but this time exactly out of step with each other. So all 3 normal modes are present in water. When it's irradiated by microwaves, the molecules vibrate, and as you saw in Unit 10, this corresponds to an increase in temperature. So the water gets hotter and hotter until it boils. Normal modes are one of the most applicable areas studied in MST 207. However, the mechanical systems usually studied are only accessible by computer.
This is why microwaves are so efficient. Microwaves are tuned to hit that resonant frequency of water. So it's like when you hit it, it rings, you know? And so the microwave is going to hit that water, it's going to ring, and the energy is going to be absorbed. Whereas if you're heating it over this is a Bunsen burner, or a flame like this, a lot of that energy is wasted because a lot of the energies can't do anything to water. It's just going to go. So like the bulk of the energy in the flame is wasted. So it's a lot less efficient. heating water. So we think about these things, but you heard about the temperature. You know, that microwave is going to hit it, it's going to cause more motion. That more motion means the temperature goes up, right? Not only does water have vibrations, but water also has rotations. You know, the water molecules can rotate. And usually microwaves will rotate molecules too. She didn't talk about the rotations of water, but the rotations of water would also happen at the microwave frequencies there. And then we have what's called translation. So the three types of motion, this is actually in your book here. I better write it down. Three types of motion would be, can somebody remind me?
Kinetic.
Well, motion is kinetic. And so three types of kinetic energy. Well, oscillations, we could have oscillations just mean you hit that resonant frequency, usually. Resonant frequency is like, how should you say? Have you seen, well, everybody in physics, I know a lot of you probably haven't had physics, but have you heard of the Tacoma Narrows Bridge? Uh-huh.
A resonance frequency be an example of like a cymatic frequency? Are those like similar things?
Cymatic frequency? Actually, I don't even know what a cymatic frequency is.
It's like sound, visible sound and matter.
Yes, it would be the same. In fact, I can show you a great example of that. The next one. So they built this impressive suspension bridge in Washington. But this is a little long, this video. So. And then the wind started blowing. So let's fast forward here to the construction. When the wind started blowing, wow, the winds hit the resonant frequency of that. And so when it hits it, then this is actually pretty important for chemistry. Those are just metal filings on a plate, and they're just vibrating the plate. You see, and so they're carrying it to different frequencies, and then seeing what happens to these filings. Observations. So what we got to do is we got to figure out, okay, do you have a hypothesis already? us being chemists, we're very interested in how matter interacts with energy. Uh-huh.
So the plate vibrating is a result of the frequency, like the noise, or the noise is a result of the plate vibrating?
The noise, the plate vibrating is a result of the noise. But I suppose if the plate were used as a speaker, it would do the same thing. Okay, I guess we're almost out of time here. Yeah, just one more minute. So let me just finish up with this. When we visualize emotion, we can visualize vibrations, and the vibrations can get kind of complicated. The vibrations aren't as simple as you might think, as you just saw for water. And then there's rotations and translations. Translations is just moving from point x1 to point x2, just moving from point to point. The coppers can't translate, and the coppers can't rotate, and so the way they absorb energy is a little different. But essentially what we can do is we can just look at heating things up and then getting them to vibrate, rotate, and translate. You don't really have to know about this resonance stuff until later. We're going to get to it. But today we end 15 minutes early, so I think it's time, right? 12:50. Double check. Yeah, 12:50. We'll end it here, and we'll start again tomorrow.